Hi guys, we are RK20 students from Unimed. Today, we are going to present our mini project which is Planet Exploration System.
Hi, my name is Chiam. Before we start present our mini project, I will briefly explain what we learned from modern control system which related to our mini project. What is control system? Control system is a device or a set of devices which are interconnected to achieve a desired purpose or output. Control system also to manage, command, direct or regulate the behaviors of other device or system. Control systems are often classified into two types. First is open-loop control system and second one is closed-loop control system, also called feedback or automatic control system. Next, the differences between leak and lag compensator. Leak compensator can increase the stability or speed of response of a system, while lag compensator can reduce but not eliminate the steady state either.
And hi, I am Nurul Syuhada Binti Ali. I will going to present the introduction. First, planetary exploration systems and space probes are always working in very extreme environment. When considering this environment and other conditions which will have significant effect on the functionality and reliability of a space problem and planetary rovers. For this project, our aims is to measure the controller to get high level of automatic controller and to explore planet and tune the controller to get high level of automatic control. Our objective for this mini project is to design fluent application of engineering tools and resources and to determine the gain and phase margin of the system, and lastly to design a compensator lead and lag.
So, our question is, an unmanned planet exploration system which requires a high level of automatic control is shown using block diagram in figure. From this block diagram, we can know that this is a closed-loop control system. Closed-loop control system is a control system which uses the concept of an open-loop system as its forward path but has one or more feedback loop or path between its output and its input. So you can know that R acts as input and then Y acts as output. The system has two functions. The first function is amplifier and controller function, and the second one function is actuator and lag function. Later, my partner will show the block graph by using Scilab software, and the reason why we draw the block plot is to show the gain and phase response of a given LTI system for different frequency.
Okay, so hi, my name is Faiz and I will be explaining on planet exploration system, which is the problem for our mini project problem. So the first problem is to draw the boot plot of the system and determine the gain and phase margin of the system. Assume K is equals to 100. So we will look in detail of the block diagram. First, for the amplifier and controller part, we have the transfer function of K S plus 1 over S plus 4, and for the actuator and leg part we have 1 over S to the power of 2 plus 6S plus 8. So that is for the cascaded version, but when we combine it we will have K S plus 1 S times S plus 4 times S plus 2 times S plus 4. We have distributed the roots of the transfer function. So for the next one, we will look in detail for the Scilab coding to generate the board plot. So for the first one, we will declare S polynomial 0S. Next one, H will be the output of the transfer function. So we'll declare a system linear S to the numerator 100 times S plus 1 over S times S plus 4 times S plus 2 times S plus 4. So for the next one, we will get the gain margin and the phase crossover frequency by the use of this coding. So for the phase crossover frequency, it will be 0.769384. For the gain margin, we will get 6.0938238. Next, we will get the gain crossover frequency and the phase margin. So for the gain crossover frequency, it will be 0.5274735. For the phase margin, it will be 25.032056. So we will show the margins on the next part. So from here we can see the gain margin and the phase crossover frequency from the red line, which represents 0.769384 for the phase crossover frequency and the gain margin of 6.0938238. And the next one is phase margin and the gain crossover frequency from the blue line, which is 0.5274735 for the gain crossover frequency and the phase margin of 25.032056. So that is all for my part. Thank you.
Hello, my name is Xinyin and I will explain about the section B of our question. Our group decided to design a lead compensator, and here are the 5 steps to design a lead compensator. First, we need to find the phase margin and the gain crossover frequency, which is found in section A of our question, which is 25 and 0.527 Hz. The gain crossover frequency is converted into radian, which is 3.31 radian per second. And then we are going to find our phi max in the second step. The required phase margin is 45, so we minus that with our current phase margin, and we plus a safety margin of 15 to get 35. Next step is to solve for the alpha, which is equation is like this, and the phi max is 35. So after we solve for the alpha, our alpha is 3.695. Next, we find our omega with this formula. To solve for the tau, we plug in the value of the gain crossover frequency and shift the equation to get the tau of 0.157. Later we'll rewrite our equation with the tau of 0.157 and the alpha of 3.695, which is like this. The final system including the lead compensators is as per this. And this is the result in the Scilab. I've plugged in the full equation, this as the numerator and this as the denominator. And after a few functions, we get that the final phase margin is 40.58. This value is lesser than the 45 phase margin we need because the gain crossover frequency is also affected. From the original 0.527, the gain crossover frequency is now increased to 0.788. That's all from me. Thank you.